Okay, thanks for hanging around this long. It's been a long day. Hopefully this talk is a good way to end. We'll have... Oh, okay. I thought I got the thumbs up. Hello. Can you hear me? Yep, that sounds better. Okay, so yeah, thanks for hanging around. Hopefully this will be a fun way to end the day with some pictures and some video and some music and some music anecdotes of us falling down pit traps trying to bolt continuations onto the CLR. I'm Jim Purbrick from Linden Lab. We make Second Life. Some of you may remember us at lang.net in 2006 when we were talking about using Mono as a new next generation runtime for our scripts in Second Life. We didn't come in 2008 because we hadn't finished, but this time we have. So it's time to come back and tell you how we got on. So in the intervening time, Second Life is now 5. Second Life is a user-generated virtual world, and that is a user-generated 5th birthday cake that was made by the residents in Second Life. There were huge parties organised by the residents. It was lots of fun. In fact, we're nearly 6 now, so it'll be 6 this summer. So this was Second Life in 2003. Each of these squares you see on the map is a region of virtual world running on a Debian Linux server. So this is Second Life when we launched it. It's something like 16 regions. Each of these regions is a fixed size, 255 meters on a side, and you can freely walk around the world. So, for example, if you start here and you walk north, when you cross the boundary, your avatar moves to a different region, and the surroundings are being simulated by a different machine. So it's unlike games like Quake and so on. It's not a single server where everyone's connected to it. It's a huge cluster of servers. It's a cloud, but it happens to be simulating a huge virtual world. So this is what's happened in terms of user hours, cumulative user hours over the last 5 years. So last time we were at lang.net, we were about here. So we've been quite busy since then, kind of scaling the infrastructure up. Lots of our work has gone there. And this is what's happened to the average concurrency of the virtual world. As you can see, it's closing on 80,000 at the end of that graph. You may notice it's sort of leveling off and getting a bit jaggy towards the right-hand side of the graph. That's where we were hitting some scalability limits. We've recently straightened some of those out, done some database optimizations, made things a bit more scalable, and so now we're back into kind of pretty steady upward growth again, which is good. So all those jagged lines are lots of stress. So this is Second Life today. There are 2 billion meters squared of land. There are 31,000 regions. There are 33 million user hours a month. In fact, we just hit 10 million user hours in a single week. So that's a big milestone. There's $1 million US of money changes hands between people inside Second Life every day. We have 8.5 billion voice minutes. So one of the things we added to Second Life is that you can have 3D positional voice chats. So if I was talking here and you were in Second Life, you would hear my voice, but you'd also hear my voice from this position. And then if Jim spoke up from the back, we'd hear that he's from the back, and we'd all turn around and we'd be able to communicate with him like that. So we have 230 terabytes of data, which is the virtual assets in the virtual world. We have 16 million people who've registered for Second Life from 150 countries, and we have 2 billion virtual items. The stat that's not on here, because this is from a kind of a non-technical talk that I stole this slide from, is that there are now 68 million scripts running in Second Life. So that's about 1,000 scripts per logged-in resident. So one way of looking at Second Life is this huge cloud. It runs scripts, and every now and again, a human being comes along and visits one of those scripts. It's also very international now. More than 50% of the people who use Second Life are not from the US, and also the demographic is a little bit older than kind of the people you'd imagine, kind of gamers with spiky hair. So we've a bunch of stuff has happened to Second Life technology since 2006, since we were last here. We open sourced the viewer. And as a result of that, we've had a lot of contributions. Things like lip sync and various other interesting interface technologies have been added to our open source viewer. One of the things that came out of the open source viewer is Windlight, which is actually the new atmospheric lighting and clouds and sky that you see in that picture there. So we open sourced the viewer. A team in Boston put their Windlight technology into Second Life. We liked it so much we bought the company, and so now it's in Second Life. We've upgraded our physics. We now have, just coming down the pipe, shadows. We have glow, which you saw on the birthday cake. You can sculpt objects. So now, instead of everything being sharp edges and boxes, you can upload sculpt maps, which deform a sphere. So you can create organic shapes in Second Life now. You can embed web pages. So you can have presentations like this in Second Life, taking slides off the web or whatever. We've done lots of work moving our server side into a service-oriented architecture, which is continuing. We had a big monolithic C++ server, and now we have lots and lots of services that you use when you use Second Life. We've started defining an open grid protocol so we can interoperate with other people's technology. We've also just started working with people on an enterprise solution for Second Life, so you can go and get your own version of Second Life, run it behind your firewall, and then all your employees can use Second Life without any information going over the web. And also, we've been working on CLI scripting, on and off. We haven't been working on it full time. So this slide is my talk from 2006. Quick recap. The video is still online. I just checked and it still works, so you can go and watch the full version of this if you haven't already seen it. But this is how scripts in Second Life work. You have primitives, which is what everything in Second Life is made up of. These are things like cubes and boxes and now sculpted spheres and so on. Basically, you add a script to your box, and then you're effectively giving a brain to that thing in Second Life. So it can then respond to people bouncing into it, touching it, and talking in the vicinity of it, and it can also manipulate the world, so it can move itself around and so on to make vehicles. So you link these prims together, these boxes and so on, to make kind of more complex structures. They have sensors and effectors via library calls, so they can go detect the avatars around me or move myself around, whatever. They can also communicate via instant message, email, XML-RPC, and HTTP, so you can hook Second Life scripts up to the web. Interesting aspects of Second Life scripts which made it more difficult to use the CLI for this. All this is untrusted code, so there are 16 million people registered to use Second Life. Any of them can turn up and start hammering code into an editor, and we'll run it for them, which is less insane than it used to be. It used to be we're the only people doing it. Now you can go and do it with Google App Engine and so on, but it's still fairly silly. We have around about 2,000 scripts per process. So we have 31,000 machines, 68 million scripts, so it's about 2,000 scripts per process. We'll run 4 simulated processes on a dual-core, dual-processor box, or I think we actually use potentially 4 processor boxes now. So we can get like 8,000 flows of control in scripts in a single box at a single time, so very high concurrency. And also we need to be able to migrate them between processes. So if you make an airplane in Second Life, you add a script so that when you click on it, you sit in the airplane, and then when you move around, it flies the airplane around. As the airplane flies across a boundary, you need to migrate that running script from one process to another. So this is what I talked about in the last talk, so I'll go through it really quickly. The way we adapted the CLI to make this work is we rewrite assemblies, and we inject code in there which effectively captures continuations of the running scripts. So we have yield points at loops and function calls, so you can't infinitely loop or infinitely recurse without hitting a yield point. When you hit a yield point, which is injected code, we go, do I need to stop because I need to move to a different process, or I've run out of time slice? And if the answer is yes, then the method will jump to a postfix. It will copy all the stuff off the stack into a heap object. It will return the method higher up in the call stack will go, is there one of these serialized lumps of serialized stack frames, or is there a stack frame object on the stack? If there is, I'll pack up and return. The whole thing unwinds. It kind of copies its stack data to a chain of objects on the heap, and then when it gets to the bottom, it goes, okay, I've done, and then you can schedule another script or move it somewhere else. So this is kind of done by inducing the stack state, which is similar to verification. For every instruction and method, you can work out what the types are on the stack. And so therefore, if you need to yield at that point, you know what you're going to pop off into an object to be able to have it as a heap object. And we inject microthreading. It's a similar process to Java GoEx and breaks, which work on Java. Then we can serialize everything, because at this point everything is now on heap. So all the objects are serializable, and then you can save it to disk to shut the machine down, or you can move it somewhere else, or you can just leave it in memory and then schedule it later on. So we migrate assemblies between application domains to unload them. So you can shut down application domains. You can unload application domains. You can't unload assemblies. But because we can migrate scripts around, we can migrate them to a new application domain and then unload the old application domain to get rid of garbage code. And we subvert the profiler in Mono to allow us to limit resources. So we only want to give scripts like a certain amount of memory. So that's basically what we talked about before. Go and have a look at the video. So some of the interesting pit traps we fell into since 2006 while we were trying to do this stuff. One of the things that the CLI has, which Java doesn't have, is managed pointers. So you can have value types which you can pass as parameters to functions. And then there are CIL opcodes, which will then push onto the stack pointers to the value on the stack. Okay, so instead of having a pointer to a heap object, which you can save that reference to another heap object. So you can copy that reference to a heap object to another heap object. This is a reference which points back into the stack, and so is only valid while that method is running. So I talked to Jim and some other people about how to do this a number of times since 2006. So what we do in the end is that we step back through the CIL in the method until we find a stack which doesn't have any managed pointers on it. Then we inject duplication opcodes and save those duplicated operands to that CIL instruction to new locals as we're going past. And then if we have to yield at the point where we've got the managed pointer on the stack, instead we save the operands to the potentially chain of CIL instructions between where the managed pointer was generated and where we want to yield. And then when we restore the whole thing, we kind of copy all these things back to locals, we load them back on the stack, we apply the sequence of CIL methods to regenerate the managed pointer back into the new stack on the new machine at a new time, and then we can just set the code running again. So this was a pain, but it mostly works. And it also works when you can potentially have chains of instructions where you go, I've got some complex value type in a method, and I've got a sequence of load a kind of pointer to a nested member of a nested member of a nested member of that object, and you can kind of just keep rewinding until you get to the point where you've got no managed pointer. So you can actually handle value types which contain value types which contain value types, and when you want to operate on some kind of pointer to a data member inside that nested value type. So this is a pain to do, but it does mean that hopefully now we're in a much better place to support C# and other languages. So the next things we had fun with was memory allocation monitoring. So the way we work out the memory used by a script is when the script is not running, so between time slices, we can walk the object graph from the root of the script object and sum the sizes of the objects it references. And so this is fine, except it turns out that even in a very small time slice, you can allocate a hell of a lot of memory if you just run a sequence of, this list equals the list plus the list again. And you just keep doubling, and after a very short number of instructions, your script is actually using a ton of memory. So a particularly nasty hack that we put in to make this work with LSL is we just limit the lengths of lists and strings to effectively, if we've got a maximum size for a script, we say, well, this is the maximum size of a list or a string that you can fit into that memory, so we just won't let you get bigger than that. And we also put a hard limit on allocation size. So we limit the size of a script to 64K at the moment, but we kind of give you a multiple of that as a scratch pad of the memory you can allocate while you're running. So, because the problem is that you might be allocating memory, but then not referencing it. So the object graph, the sum of the object graph size is smaller than the allocation size. So we let you allocate past the amount of memory we let you use. And then once you've yielded, we then walk your object tree to make sure you're back underneath the size limit that we want you to have. So exceptions would have been much better here. So the way we do it is that because we didn't want to use exceptions because they were fairly slow in Mono when we first started, at yield points we kind of call back into unmanaged code to say, do I need to yield now? It would have been much nicer to handle this stuff, to be able to go throw an exception at any point, and then have a catch, have an exception catching mechanism to do the do I need to yield now stuff. Because then effectively you can have the memory allocation profiler throw an exception to say, hey, you might be over your memory limit now. You should yield right now and check your memory size because you might be over. But we can't do that. So instead we have this scratch pad. Another consequence of this is that you can have lucky scheduling, which gives you temporary memory boosts. So for example, if you're doing this kind of list concatenation thing, because there's value semantics in our scripting language, LSL, you can end up with lots of situations where you have, for example, this list equals this sublist. And so while that expression is being evaluated, there are two copies of the list because it's the language has value semantics. And so that means that you fairly often shoot over your memory limit while you've got two copies of that potentially big list. And so then you're into the kind of the buffer between the memory limit and the allocation limit while you're doing that operation. So it would have been nicer if we could have just gone, the allocation profiling code could have just thrown an exception to say, you might be over your memory limit, so pack yourself up now and we're going to measure your size right now. And then there wouldn't have been this kind of like overlap between the time at which you allocate too much memory and the time at which we can actually check how much memory you're using. So that's kind of a little bit scruffy still. So that was kind of fun. So scheduling is also fun. We check the time at the yield points. It turns out that the system call gates the execution really, really quickly. So in our old code, our old interpreter was really slow, so the overhead of checking the time often was pretty low. But when you're using jittered monocode, you can actually run a ton of code really quickly, and actually calling out to the system to say, what's the time do I need to yield? Takes ages. And also, the execution time may vary widely. So depending on the library code you're making, if you're giving it a huge list to operate on and you want to sort it, for example, depending on the list length, that library call will take a varying amount of time. So what we do instead is we do adaptive timer skipping. So to start with, we check the time at every yield point, but if we're consistently checking the time too often, for example, we're checking the time 100 times per time slice we want to give the script, eventually we'll start skipping timer calls. And we'll keep skipping timer calls until we skip too many, effectively. So we have a kind of almost a TCP back-off algorithm for adapting the timer skipping based on the script. And it works really well. We end up with, it gives us a massive multiplier in terms of execution speed because we're skipping most of the timer calls we used to make. But it does make for amusing flywheel exploits by our residents, who then effectively just go, okay, I'm going to write a script which sits in a type loop, spinning, doing nothing, and gets a huge timer skip because it's skipping over all these yield points, building up this enormous timer skip value. And then they go, right, now we've got a really big timer skip, sort this enormous list, which then skips over, sits in a loop doing a really expensive operation, which then skips because it used to be in this really tight loop, and so then you end up with it shooting past the end of its time slice, and so then you have to kind of come back and spank it later and say, right, you're not running for ages now. But because we're trying to do this in a system which is trying to do 45 frames a second of simulation, that can be problematic. So yeah, that's kind of the current thing we're scratching our head over at the moment. The other thing we found is that marshalling is our new bottleneck because we've effectively got two scripting engines now. We've got the old one written in C code that interpreted our proprietary bytecode, and then we've got mono. In order to avoid having two copies of the same set of library calls, we've still got all the library calls implemented in C++. And so that means when you need to do a library call, you effectively have to do things like take big managed array lists and copy them across the boundary to C++, so you can then have the common library function code that's shared by both virtual machines operate on the stuff. So we now find that converting big lists back and forward across the boundary is the big expense. So hopefully what we'll be able to do fairly soon is stop supporting the old virtual machine, which will mean that all new features only need to be implemented in managed code for mono. And then that means we could start re-implementing the expensive list operations just in managed code to avoid those kind of transitions. So this is the this is the really crazy one. So managed execution after a segmentation violation. So really close to the end of this, we thought we'd got pretty much all the bugs ironed out of this and everything was going to be great and we were just about ready to ship it. One of our engineers realized that, that when our simulators were crashing, they were no longer saving an emergency sim state. So what used to happen, or what does happen in Second Life, is when a simulator crashes, it tries to serialize its state in its signal handler, which is a fairly, it's a fairly crazy thing to try and do. It kind of works relatively well when you have scripts which are just self-contained 16K blocks of memory, which is what our old scripts were. Okay, when they're not executing, they're just a block of memory. There's nothing complicated you need to do there. So you just cross your fingers and go, okay, we've crashed, but we're going to try and copy this block of memory to disk, and hopefully it'll avoid content loss. People who've built stuff in Second Life and then their simulator has crashed. And so now that some of our scripts are mono, we have to do more work. They're not just a contiguous block of memory in the process. They're proper objects that are dynamically allocated and have references to each other. So effectively, we have to run managed code to serialize that blob serialize that graph of objects into a blob that we can write to disk. And so in order to do that, we had to change the way Mono handles signals, because Mono uses signals to do null reference exceptions and so on. So what we found was that we'd embed Mono, and then none of our signal handlers would get called anymore. So, and this was a few weeks before we were trying to ship this thing. And so effectively we had to implement signal chaining for Mono. So we had to go in the Mono runtime. It's actually a little bit, it's frustrating because we'd managed to go kind of like several years without ever changing any Mono code. And then all of a sudden, just before we shipped, we had to change the Mono runtime to change the way it did signal handling. But luckily it's an open source system, so we could do that. So we implemented signal chaining in Mono so that basically the signal handlers in Mono would go, am I in managed code? If so, do the Mono thing. If I'm in unmanaged code, because there's been a segv in the C++ or whatever, chain to the original simulator signal handlers, and then the signal handlers would then potentially call back into Mono after this segmentation violation to call the serialization code to turn a script from a graph of objects into a serialized block that we could then write to disk. And so in order to do that, we had to turn off the Mono garbage collector, which really didn't like running after a segmentation violation of concern. But we're in the process of crashing here, so garbage collection is the least of our worries. So we'll just go, right, the garbage collector doesn't like working after this segmentation violation. We'll turn it off, and then we'll call back into Mono, get it to serialize these scripts, cross our fingers, write a block of data to the hard drive, and then crash. So we got that working. And we've ended up contributing that signal chaining implementation back to the Mono project. So that's currently being used for Moonlight. So that's great. It was very close. Yep.
Just curious, these segvs, are they coming from your internal libraries that the scripts are calling into?
So the segvs, for the most part, are coming from buggy C++ code. So we have a crash rate for the simulators. So most of the time, something happens in the simulator, a segv happens, and we need to call our signal handlers, do this emergency sim state save, and exit. Most of the time, those segmentation violations are nothing to do with Mono, but we need to route those signals back out of Mono and into our application, and then we need to, from that signal handler, route back into Mono to tell it to serialize all these scripts that are hanging about in memory and now need to be written to disk. So those were the kind of amusing pit traps and anecdotes that we encountered over the last few years while we were trying to ship this. And this is what the final thing looks like. So this was the original virtual machine. And this is the same script running on Mono. And it's effectively calculating and rendering fractals. Both of these screens are kind of grids of boxes in Second Life, and the script's changing the color of the boxes to effectively act as a display. As you can see, the original scripting engine is still crawling its way through the first frame, and the mono one, we're able to click on it and interactively explore the fractal. So the two things this video shows, first of all, this one's running a lot faster, but second of all, you know, the kind of increase in speed is turning something that wasn't interactive before into something that's interactive, right? I'm just watching this render, whereas I'm able to explore this thing and kind of get it to recalculate a display in real time. And so, okay, I'll turn the, sorry, the sound is actually Mandelbrot set by Jonathan Coulton. So it's quite funny, I recommend it. Yeah, so this is a kind of a contrived example, because it's doing something mathematically complex, and it's showing pretty much the maximum speed up you can get from running scripts on mono and compared to the old scripting engine. But you could imagine this, instead of drawing fractals on a 2D screen, you could imagine this kind of visualizing SQL data in a 3D environment with 50 people looking at it. And kind of talking about some kind of analysis that's being done on some data or whatever. And so, although effectively at the end of this we've mostly got a scripting engine that just runs faster, we've actually got kind of different applications that can be built in Second Life. In addition to the speed up, we also save quite a lot of memory, because the old virtual machine would allocate a block of memory for a script that was 16K in size, regardless of how much of that memory you used. Whereas the mono virtual machine will just allocate data as you need it. So on average, although mono scripts can use up to 64K for an equivalent script, they tend to use on average about 9K. So we save kind of 30 odd % of our memory compared to the old scripting engine. So the future, and this is kind of pretty much the same future I talked about 3 years ago, but hopefully we can actually get to it now we've shipped the first bit. So it would be great to have C# and F#. Nearly the whole of this work is language agnostic, right? So we've got a compiler that compiles our scripting language LSL down to a .NET assembly, but then all the assembly rewriting stuff to do the microthreading can work on any assembly, and the only way in which we've changed the virtual machine to make this work is by contributing signal chaining to mono. So this stuff still works on the Microsoft VM, and it also works with any language, in theory, any language on any assembly. We actually have a proof of concept of C# scripting in Second Life, where we basically just, instead of calling our compiler, call the mono C# compiler, and then everything else is the same. So C# and F# would be great. IronPython and IronRuby would also be great, except all of Jim's cunning work with the DLR has made this much more difficult, because for these languages, you just get an assembly and you rewrite it. Whereas for the DLR, it's busy doing crazy things with dynamic methods all over the place. And so in order to get the continuation stuff to work with IronPython and IronRuby, we'd need a hook into that, so that when IronPython's going, I'm going to create a new dynamic method or whatever, we're going, can we have a look at that and monkey with it, please, before you start running it? So we'd like to talk about that. Yeah.
IronPython and IronRuby, they generate an expression tree.
Yep.
Couldn't you take that expression tree and monkey with it and then generate whatever back-end code you wanted from it?
Yeah, probably. So there are probably ways in which we can make this work with IronPython and IronRuby, but they're different to the things we've had to do to make this work with LSL, our scripting language, and C#. So I would love to talk about that and find out the best way of making that work and how much work that would actually be. So the other things we can do is we can have resource pools, because scripts now allocate memory dynamically. There's no reason to go, your script will be 16K. So there are lots of applications in Second Life where you just want to go, right, I want 4 megabytes of memory. I want to suck a load of data in over the web and do some kind of analysis of it or visualization of it. So that's an easy one. Libraries and APIs is going to be good. LSL doesn't support any way of saying, include this library or other API. When we have C# and other .NET languages, it would be great to be able to say, first of all, residents can create their own libraries, because then people can build could then build object-oriented APIs on top of our kind of flat, effectively set of static methods that you use for interacting with Second Life at the moment. APIs would also be interesting, because you can imagine where you have Second Life running in an enterprise, it has APIs for connecting to LDAP or databases or whatever enterprise systems you have. So you can have scripts that go, kind of I want to use this library, and where it exists, it works, and where it doesn't work. Whereas at the moment, everything has to be available to all scripts. So it would allow us, different APIs would allow us to kind of differentiate, kind of Second Life running in different environments with different resources available to it, and scripts would be able to kind of do the right thing. IDE integration would also be good. There were some people at LangNet 2006 talking about Visual Studio Express as having a Second Life project type. That would be great. I would love to talk about that again, now that we've got this stuff done. Very recently, there's been some talk about mono continuations. So there's a mono continuations extension. Mono is now embracing and extending .NET, which is kind of amusing. And they have support at the moment for continuations within a single process. So, and they do it much more efficiently than we do because they're in the VM. They can just go, throw this stack away and switch this stack in. It would be really cool if we could integrate their work with this, so that when you're scheduling between scripts in a process, you're just flinging stacks around, and you're only doing this full heavyweight, kind of serialize everything to the heap and turn it into a block of memory when you want to ship it to a different machine or to disk, and that would speed this stuff up a lot. We should at some point use generics and Cecil to do our rewriting. At the moment, we're not. So we end up generating tons and tons and tons and tons and tons and tons and tons of classes for every method. Many of those classes, you'll have many methods that have 4 integers as their locals. And so really you should just use generics and use generic sharing, which is now implemented in Mono, so that it's actually the same class. When you have 4 blars, it's using the same stuff on disk. It would also be really cool to try and contribute some of this stuff back. So if we ended up finding a good way of making our stuff work with the mono continuations work, it would be really good to be able to kind of contribute our kind of heavyweight continuation stuff, and then have kind of both available transparently, because they've got pretty much the same API, so that when you're running on Mono, your code is using the Mono VM switching. When you want to migrate to a different machine or save to disk, you use our code path. And also potentially when you're running on the Microsoft VM, which doesn't have the VM level continuation support, it runs our code as well. And then you can run the same application on Mono and the Microsoft VMs and have continuations in both places, which would be fun. So last slide, conclusions. Using the CLI to run untrusted code in the cloud is possible. I'm not going to say it's easy, but it is possible. There's more to it than running untrusted code. It's not enough to have a sandbox and go, there you go, ta-da, you can't monkey with my system. It's like, well, no, I can't monkey with your system, but I can use up all your memory and sit in a tight loop and effectively do a denial of service attack on your machine. So you need to be able to do that kind of resource allocation management as well. Assembly rewriting is really powerful. And it would be great if we had ways for getting IronPython and IronRuby and the DLR languages to spit out assemblies when you want to, so that you can then do this rewriting, and you can treat all the languages the same in terms of, they're all just things that spit out assemblies. Now, obviously, you're not going to be able to have all of the facilities available for those languages if you do that, but I think IronPython used to create assemblies and now it doesn't, or something. So.
But it's a very weird mode for a dynamic language that's running.
Yeah, I'm happy with weird modes. I think there are people who would like to use Python, and if we could get a fast way of using Python in this environment by getting it to spit assemblies out, then that would make them partially happy, not completely happy. So thanks for listening. I'm Jim Purbrick. In Second Life, I'm Babbage Linden. I sometimes blog at Linden Lab, and I also blog at home. So thanks for listening. Any questions?
Why does Second Life still run at 7 frames per second?
On your client? Well, I don't know. Are you running Windows?
But I had telegraph.
Right. So Second Life has an extremely different way of working. So we're getting kind of off topic here. Second Life has a very different way of rendering 3D graphics to most other 3D applications. And by that, I basically mean games. Most of them render very few very complicated meshes. So, 30,000 polygons at a time. Because of the way Second Life is set up, it ends up rendering kind of tiny little cubes and boxes and so on. Now we are doing work to make that better by kind of coalescing stuff and figuring out stuff which doesn't change. But But yeah, our priorities at the moment are scaling up the system and making the user interface better. So we will get to client-side rendering performance. But I mean, if you're careful and you buy the right hardware and et cetera, you can get Second Life running with 60 frames a second in huge resolutions with all the bells and whistles turned on. So yeah.
So I should mention, I mean, yes, you have some really hard problems, right? CLI in the cloud does run every day with ASP.NET, with untrusted code. It's not, the demands on it are not as harsh as yours, right? So I just would love to see your conclusion change to running CLI in the cloud in extremely demanding situations as possible.
Okay, fine, deal, done. Yeah, well, I'll change it later. Yeah. Anyone?
Will we see the demo?
Huh? So last time, what? Well, so last time the only way we got demo running was using the Xbox 360 internet connection. So I wasn't sure that was going to be available.
I hope that there's Wi-Fi at Rock Bottom.
Pardon?
I have to hope there's
Yeah.
Wi-Fi.
Yeah, we'll do it this evening. We'll do it this evening. In the bar, we'll find some public internet without a firewall, and then we can do a demo there. Any more?
Which technology are you using to inject into assembly to write assemblies?
So we're currently using an academic framework, which is not currently supported, so we're effectively maintaining it. Since we did this work, the Mono team have added Cecil, which is a really powerful assembly rewriting library that supports generics and all the rest of the stuff, and which Mono actually use as part of their build process to effectively slice down assemblies to make limited versions of it for Moonlight. So it would be great to move our stuff onto that at some point in the future, and we'll need to do that when we want to have this use generics and have bytecode sharing between the stack frame classes, because otherwise we're going to have to add that support to the framework we're using, which would be a ton of work. Any more? Okay, thanks for listening.